Welcome to lesson 5.2. Today we're going to look at three gas laws. We're going to look at Boyle's law, Charles' law, and Avogadro's law. And I do apologize, these PowerPoints contain a lot of derivations and graphs and how they got to these laws, where most chemistry students just want to look at the law and use it in calculations and in conceptual questions. What happens if this, if you do this, what happens? So anyway, we'll work our way through this. We're going to start off with Boyle's law. Boyle is actually attributed with being the father of experimental chemistry because he did a lot of experimentation, took a lot of notes, was very good at documenting things and holding things constant. And one of the things he studied was the relationship between a gas's pressure and its volume. And he found that a lot of, in his measurements, that anytime he took pressure times volume, he got a constant. This tube is similar to what Boyle used in his experiment. And if you'll notice, this is what he found. He found that so he would change the pressure and have different volumes, and then every time he took those times each other, he ended up with basically the same number. And so when we have that equation that says PV equals K, that's what he's talking about. And how Boyle knew to multiply those numbers together, he was just kind of looking for a trend. That's a lot of what science is. You just take your numbers, manipulate them, and you're like, oh, that's what that means. So a couple different plots that Boyle did, a lot of different mathematical applications. You see the equation of a line there. And so when he plotted pressure versus volume, he got something like that. And when he plotted volume versus 1 over pressure, he got a straight line. Boyle, Boyle, through his experimentation, knew that an ideal gas strictly obeyed his law, and an ideal gas behaves in such a way that the molecules of the gas don't interact with each other, don't cause any kind of either adhesion or pushing away. And so he used that ideal gas law to predict or to plot pressure, volume versus pressure for several different gases. And so the ideal gas law is here. Notice that a noble gas, which is very unreactive, is actually above that. And these gases which have more electron density and electronegativity, maybe a little bit of polarity, are below that line, so they don't behave as ideally as the ideal gases. So let's use Boyle's law to do a problem, and Boyle's law is normally written P1 V1 equals P2 V2, and so these are your initial conditions, and these are your final conditions. With Boyle's law, we don't have to have any particular units. We just have to have the same units on both sides. So if you're measuring pressure in pascals, you need pascals on both sides. Measuring volume in liters, you need to have liters on both sides. So if we have, these are our initial conditions. We have a sample that's at 5.6 times 10 to the third Pascal. We're going to take that times the initial volume of 1.53. What does that change to? It changes to 1.4 times 10 to the fourth Pascal. And so what is that final volume that we're looking for? And so if we manipulate, we're going to take 5.6 times 10 to the third times 1.53, and we're going to divide that by 1.5 times 10 to the fourth, and we get a new volume of 0.57 liters. And we're going to use two significant figures there because there were two and there were two as well. So just running it through on the PowerPoint slides. So there's that useful form, and that's the form that you'll need to have memorized. Solve, and we got 0.57 liters. Does that make sense? Because as pressure increases, so pressure and volume are inversely related. So if one goes up, the other one should go down, and we increase the pressure, so the volume should have went down, and it did. So with gas law problems, especially these simpler ones, you should be able to check your answer at the end to see if it makes sense. Another example, we have an aerosol can that has 400 mils of compressed gas at 5.2 atmospheres. We're going to spray that into a large plastic bag, which inflates to 2.14 liters. So here are our volume measurements. We need to convert this one to a liter measurement, and then we can plug it into the formula. So our initial condition was 5.2 atmospheres times 0.4. And notice I'm leaving the zeros off because I'm kind of doing this helter-skelter. And then I'm going to run that math. I'm going to take 5.2 times 0.4. Then I'm going to divide that by 2.14, and I end up with a new pressure of 0.97 atmospheres. Okay, what did I do to the volume? The volume went up, so the pressure should have went down. Started out at 5.2, went to 0.97, it went down. And they used one more significant figure, which I should have added on there because 3 sig figs, 3 sig figs, 3 sig figs, so 0.972. And so Boyle did a lot of experimentation with gases, and so he used ammonia, which is not anywhere close to being an ideal gas because it's a polar molecule, and tried to calculate K with that. And so here's his experiment, and there are the values he got when you took pressure times volume. Notice they are close together, not perfect, but close together. The pressure changes in one direction. Notice that when he did this experiment at 0 atmospheres, the K was 22.4. You'll find the same plots with other gases, carbon dioxide, oxygen, even noble gases. So the important part to take home from the Boyle's law is making sure that you know how to do P1V1 equals P2V2, and knowing that pressure and volume are inversely related, because there was a lot of extrapolation in there in terms of his research. The second law we're going to talk about is Charles' law. Jacques Charles, a French physicist, looked at the look what happened to a gas, or the pressure of a gas. Volume of a gas when you change temperatures. Now, you have to be very careful on this one, and we'll talk about it here in discussion questions shortly. And in this one, you can have your volumes in any particular volume unit, but you must have your temperatures in Kelvin. There's his plot of temperatures versus volumes. And notice where it crosses right here. That's how we know, or we can predict what absolute zero is, because on this planet we have not ever reached absolute zero, but we can predict what it is based on Charles's research. Again, we're going to kind of look at what Charles did in his research, where he had the constant, and again, that won't be as useful to you, but this is how he came up with his law. So this is what I mentioned earlier. Why do we have to have that in kelvins? What if we had it in Celsius? Well, Charles's law is actually written like this. If you have a gas at 0 degrees Celsius, it occupies some volume, but if you put a 0 down here, then mathematically that doesn't work. And so we have to have all motion cease at absolute zero, so it makes more sense to have that in Kelvin because it fits with the definition of kelvins, and we'll talk more about that when we talk about kinetic molecular theory. A sample of gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.58 liters. Notice the pressure doesn't change, so we don't have to worry about that. So we are going to use Charles's law. But the first thing we have to do is we have to change these Celsius temperatures into Kelvin temperatures. And then we can plug them in. And we come up with 2.79 liters. It's greater than the original volume, which is good because the temperature increased, and so we would expect the volume to increase as well. So the takeaways from Charles's law are V1 over T1 equals V2 over T2, so that's our thing. T has to be in Kelvin, and these things are directly related, which means if I increase one, then the other one's going to increase as well. So those are your takeaways from Charles. The last law we're going to talk about today is Avogadro's law. Again, Avogadro did the same kind of experimentation where he came up with a constant and so on, a proportionality constant. But what he looked at was if you hold pressure and temperature constant, what happens to the volume as you increase or decrease the moles of gas. So each of these balloons holds 1 liter of gas at 25 degrees Celsius and 1 atmosphere, and each balloon has 0.041 moles of gas. So they're all going to have the same volume because they have the same moles. What if we had a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and temperature of 25 degrees Celsius? So notice it says same temperature and pressure, so we don't have to be concerned about those. What would be the volume of ozone? So V1 over N1 equals V2 over N2 would be the equation that we would use. My apologies, I guess I didn't read the question carefully. If O2 were converted to ozone, so we also need a balanced equation. And so we have a 12.2 liter sample that starts off with 3 moles, and we're going to we don't know the volume of sample, that's 2 moles, so it should decrease. That's why we need that balanced equation. So there is our second volume. So our number of moles decreased, and so our volume would decrease as well. So again, the takeaways from Avogadro's law, here's the formula. We don't have to manipulate anything, so because moles are just in moles, volumes can be in any unit. We just decide that and make sure they're both the same, and they are directly related, so that's another takeaway. If 27.1 grams of argon occupies a volume of 4.21 liters, what volume will 1.2 moles of neon occupy at the same temperature and pressure? So gases are going to behave the same regardless of their identity. If we already have moles of neon, but we don't have moles of argon, so we'll have to figure that out. So 21.7 grams of argon. How do we get to moles? We use the molar mass from the periodic table, which is 39.9 grams of argon and 1 mole of argon. And if we do that calculation, we end up with 0.679 moles of argon. Whoops, my apologies. So we plug that in. If we have 4.21 liters and 0.679 moles, and we put an X in for that, and we have 1.29 moles. So 4.21 times 1.29 divided by 0.679, we have 7.9. Actually, we're going to go with 8.00 is what I'm going to go with, liters. Notice it's a little bit different here. They probably use a different molar mass for argon, but it's close enough. Okay, we did increase the number of moles, and so volume should increase. A balloon contains a certain mass of neon gas. The temperature is kept constant, and the same mass of argon gas is added to the balloon. Okay, so we got neon gas, which has a molar mass of 20. Argon has 39.9. What happens? So if we add more moles, we know that the volume's going to change, and so we can get rid of this one. Moles is directly related to volume. If one of them is 20 and the other is 39.9, this one is not quite double of the first one, so we know it's going to expand, but it's going to be a little less than 2 times. It's not quite going to get that big. Each of the balloons holds 1 liter of gas. All are at 25 degrees Celsius, and they have the same number of molecules, so they have same moles, they have same temperature, they have same volume. So what also would have to be the same for these? Well, the other thing we talked about was pressure. So if they have the same volume and the number of moles and the same temperature, then the pressure is going to have to be the same as well. A cylinder is fitted with a movable piston. Pressure inside the cylinder is Pi, which means initial pressure, and the volume is Vi, which means initial volume. What's the new pressure in the system when the piston decreases the volume of the cylinder by half? So if we have the initial, it needs to equal the final. So here's our initial, and let's just assign 1 as the constant. That's what that equals. And so if I decrease the volume by half, what has to happen to the pressure in order for that to still equal 1? Well, I need to take it times 2. And so the correct answer is going to be C on that one, because if I decrease the volume, the pressure is going to double. And that concludes lesson 5.2. The next lesson will be about the ideal gas law.